Welcome to the deep dive. Some of the biggest environmental challenges we face today aren't always the ones that grab the headlines. They're often hidden, an unseen legacy woven into the very fabric of industrial processes.
Yeah, lurking beneath the surface, so to speak.
Exactly. And today, we're taking a deep dive into one of the most persistent, costly, and surprisingly widespread of these challenges: acid rock drainage.
Or its close cousin, acid mine drainage, AMD.
It's a problem that originates from mining, certainly, but its impact can ripple through communities and ecosystems globally.
Oh, absolutely. And often persisting for centuries, which is quite staggering when you think about it.
That's why we wanted to tackle it. For this deep dive, we've gone straight to what feels like the authoritative source. Chapter 22, Acid Rock Drainage, the Unseen Legacy.
From Mining and the Environment by Spitz and Trudinger. A really solid text.
It is. Our mission today is to give you a quick yet thorough understanding of this complex issue. We want to explore its origins, its surprisingly far-reaching impacts.
And the solutions, which are often ingenious, but also, frankly, sometimes frustratingly difficult.
Yeah. Our goal is for you to walk away with some surprising facts and those aha moments without ever feeling overwhelmed. Okay, let's unpack this.
Sounds good. So, at its heart, acid rock drainage, ARD, happens when certain sulfide minerals get exposed to oxygen and water.
And then these sulfides are common. Really common.
Incredibly common. Things like pyrite, pyrrhotite. You find them alongside many different types of ore. And when they oxidize, well, they produce acidic solutions, basically sulfuric acid.
And acid mine drainage, AMD, that's just when it comes specifically from mine workings.
That's the distinction, yeah. AMD is ARD from a mine.
Okay. And it's not just the acidity itself that's the problem, is it? There's more to it.
No, that's a key point. This is where it gets really concerning. These acidic solutions are really good at dissolving heavy metals.
Like what kind of metals?
Things like copper, arsenic, lead, zinc, you name it. The acid makes them mobile.
Mobile and, crucially, bioavailable.
Exactly, meaning they can easily be absorbed by living organisms. It's like this hidden multiplier for potential environmental damage.
Wow. So where does this happen? Is it everywhere?
It's very prevalent. The potential exists at most gold mines, major copper mines, many silver, lead, zinc, nickel operations.
Even coal mines.
Yeah, even coal mines, because pyrite, that iron sulfide, is frequently present within the coal seams themselves, or in the rock layers around them, the overburden and interburden.
But it's good to know it's not absolutely every single mine, right? There are exceptions.
That's true. If a project is only mining already oxidized ores, think lateritic bauxite for aluminum, or lateritic nickel, iron ore, manganese mines, then ARD typically isn't a concern. Same for some near-surface gold or copper operations that are already oxidized.
That's a really important distinction. And within a mine site that does have sulfides, ARD isn't just coming from one place.
Oh, definitely not. It can emerge from runoff off surface excavations like roads, drains, drainage pumping out of underground workings.
Seepage from pit walls.
From the walls, the floors of open pits, yeah. Seepage of contaminated groundwater moving through the rock mass, even from those fragmented rock masses created by methods like block caving.
What about the stockpiles or waste rock?
Absolutely. Runoff and drainage from ore stockpiles, from waste rock dumps, seepage or overflow from tailings storage facilities.
Tailings are the processed leftovers, right?
Exactly. The finely ground rock after the valuable minerals have been extracted, and even small spills of mineral concentrates can contribute. It's quite pervasive within an operation.
It's pretty remarkable to consider that this problem affects virtually every corner of the mining world.
It really does. You need moisture and temperature, sure, but there's enough moisture pretty much everywhere.
And the temperature thing, even if it starts slow in the cold.
The reactions themselves actually generate heat. So once they get going, they can rapidly accelerate the oxidation rates, even in colder climates.
So we've seen severe examples everywhere, from arid Australia
to the Canadian Arctic, yeah. And equatorial Indonesia. Nowhere is really immune if the sulfides and the conditions are right.
Okay, but here's something that surprised me from the reading. ARD is fundamentally a natural process.
It is. At its core, it is. Sulfide minerals, especially pyrite, are incredibly widespread in nature. You find them in organic clays, silts, peats, shales, coal, schists, phthalite. all sorts of rocks.
So naturally, when these minerals meet oxygen and moisture, they can oxidize.
Correct. Natural groundwater near sulfidic mineralization can definitely be acidic, especially in the unsaturated zone above the water table where oxygen is present.
The source mentioned an example in Indonesia, air merah.
Yeah, red water. Near the Batu Hijau copper deposit. It was a spring-fed stream, pH of 4, high manganese and copper. And this was before any major mining began there, a natural phenomenon.
So if it happens naturally, why is it such a huge problem when mining gets involved? What's the difference?
That's the absolute core question. In nature, the oxidation rates are usually very low. Any acidic groundwater that forms tends to get diluted or neutralized naturally over time and distance.
So you might not even notice it, except maybe higher sulfate levels.
Often, yeah. High dissolved sulfate might be the only clue that sulfide oxidation happened. Mining, though. Mining exposes vast quantities of these minerals all at once to air and water.
Oh, okay.
It dramatically amplifies the rate and the scale of the process, and that's where the problem truly begins. It overwhelms the natural buffering capacity.
It makes sense that this isn't an instant thing, but something that develops. The source broke it down into 3 stages: oxidation, leaching, and drainage.
That's a good way to think about it, yeah. A clear progression. Stage 1 is oxidation.
Yeah.
This is where those sulfide minerals, pyrite, react with oxygen in the presence of water. And there's a key indirect mechanism that's, well, destructive in its cleverness.
Go on.
Pyrite oxidizes to ferrous ions. Those then oxidize to ferric ions. And these ferric ions then further oxidize more pyrite.
And that releases heat, you mentioned earlier.
It does. And you often see the visible result, the precipitation of those ferric ions as hydroxides. That forms the characteristic sort of brown, slimy sludge you might see in affected areas.
Like rust stains, almost.
Very much like that, yeah.
And don't bacteria get involved here, too? Speeding things up.
They absolutely do. The oxidation rates shoot up at low pH, and they can be significantly catalyzed, sped up, by bacteria like Thiobacillus ferrooxidans.
So it starts slow.
Often, yeah, it can take months, even years, with a gradual drop in pH, but once that pH drops below about 3.6, boom, there's a sudden rapid acceleration in the oxidation rate.
And the sulfuric acid that's formed then attacks other minerals.
Exactly. It's highly reactive. It dissolves metals from adjacent minerals and forms these soluble sulfate salts, things like gypsum if there's calcite around, or various minerals called jarosites.
Okay, so that's the oxidation.
Yeah.
But the acid itself just sitting there isn't the main issue. It needs to move.
Precisely. The oxidation products building up isn't the immediate environmental problem. It's when those acidic products get flushed out, leached, and then discharged into the environment. That brings us to stage 2, leaching.
Which is mostly driven by rainfall.
Mostly, yeah. Rainfall flushing through the oxidized material. And in arid or seasonally dry climates, you often see ARD happening in
Pulses.
Yeah, tied to specific rainfall events. The highest acidities and salt concentrations often come with the first significant rain after a long dry spell. It flushes out everything that's built up.
Right, like a concentrated slug of pollution.
Pretty much.
Okay, so oxidation, then leaching. And finally, stage 3 is drainage, how it actually gets transported out.
Right, how it moves into the receiving environment, rivers, lakes, groundwater. The common pathways are things like mine dewatering, pumping water out of surface or underground mines.
Rainfall runoff in open pits.
Yep. Seepage from waste rock dumps or stockpiles, often coming out from the toe, the base of the pile.
And from tailing storage facilities, too. Seepage or overflow.
Definitely. And another pathway, maybe less obvious, is capillary rise. Water wicking upwards, especially on the surface of tailings or fine-grained waste rock dumps.
Wow. So many potential sources within just one operation. It's quite the challenge.
It really is.
So we've covered how it forms. Let's talk about the actual real-world impacts. The source mentioned that sometimes the acidity can stay isolated within a mine site, which is good.
Yeah. If it doesn't connect to external water bodies, the immediate environmental concern might be lower, but often it does contact aquifers, groundwater systems that eventually discharge to the surface.
And that could be years, even decades after mining stops.
Easily. Though natural neutralization and dilution in the groundwater path can sometimes mitigate the effects, thankfully.
But when it does cause problems, what are we looking at? Impacts on the mine itself first.
Yes, definitely. Direct impacts on operations. We're talking about serious corrosion.
Corrosion of what?
Concrete foundations, culverts, metal pipes, walkways, anything susceptible to acid attack, it just eats away at infrastructure.
I remember reading about a nickel mine in WA, Western Australia, where pyrrhotite oxidation caused rock bolts, holding up the tunnels to fail in just 2 months.
That's right. Huge safety hazard. Imagine the roof collapsing because the bolts corroded away.
Terrifying.
And it's not just structural failure, you can get air quality issues too.
How?
In some open pits, like North Davao copper in the Philippines or Metnewman iron ore in WA, you can actually get sulfur dioxide fumes generated from the pit walls oxidizing.
Like volcanic fumes.
Yeah. If there's no wind, these heavy fumes can settle in the bottom of the pit. Creates a serious air quality hazard for workers down there.
And there was something about rocks physically breaking down.
Yes, physical disintegration. It happens when sulfate salts crystallize inside tiny cracks and pores in the rock. The crystal growth exerts pressure, like ice wedging, and can break the rock apart. This could damage structures like retaining walls or even rock-filled dams built with that material.
Okay, those are the operational impacts.
Yeah.
But the really big ones are ecological, aren't they? Especially in fresh water.
Absolutely. That's where the most serious effects are usually seen. ARD can certainly damage plants or soil it flows over directly, but those terrestrial effects are usually pretty localized.
But rivers, streams, lakes, they can be affected.
Much more broadly. This is where it gets particularly problematic. Most aquatic organisms, fish, insects, plants, they're adapted to neutral or maybe slightly alkaline waters.
So any increase in acidity is bad news.
Even a small increase can adversely affect the local aquatic life, yeah. The extent of the damage really depends on a few things, like the sheer quantity of ARD, how acidic it is, what metals are in it, and how concentrated they are. Also, how well the mine can actually contain it.
And the receiving environment matters too, right? Its ability to cope.
Hugely important. The assimilative capacity. Can the river dilute it? Absorb the metals, neutralize or buffer the acid, and of course, how sensitive are the local organisms to begin with?
So what actually happens to the ecosystem at different pH levels?
The impacts are usually worst right near the discharge point, and then they lessen downstream as dilution happens. If the pH drops below 5, you'll see a big drop in biodiversity. Fewer types of plants, fewer aquatic invertebrates, especially insect larvae, which are often very sensitive. Fish might survive but could be stunted, or their breeding might fail. And below pH 4, it gets really bad. Most life forms die off. You're left with only very specialized bacteria and algae that can tolerate extreme acidity.
Wow. And you mentioned something interesting earlier about the buffering capacity suddenly being overcome.
Yeah, a water body might cope for a while, neutralizing the acid, but then it hits a tipping point, its buffering capacity is exhausted, and the pH plummets rapidly. You get this sudden, drastic deterioration.
So these ecosystems are constantly shifting.
Often, yeah. Especially if the ARD discharge varies, like with those rainfall pulses. You can get periodic kill-offs, followed by some partial recovery if organisms can recolonize from unaffected upstream areas or tributaries. It's a very stressed system.
What about the sea? Is it less vulnerable?
Generally, yes. ARD discharges directly to the ocean are relatively rare, actually. And when they do happen, the effects are often localized.
Why is that?
Seawater has a huge buffering capacity, much larger than most freshwaters. Plus, there's constant circulation and dilution. The examples from Tucapalaquahone in Peru showed tailings buildup was unsightly, but marine life wasn't much affected beyond the immediate area.
And Tasmania, Macquarie Harbor.
Despite decades of tailings discharge from Mount Lyell, the harbor still supports a productive fishery. But, and this is key, the freshwater rivers upstream of the harbor, the Queen and King rivers, suffered far more severe, long-lasting damage. It really highlights the vulnerability of freshwater systems.
Okay, so ecological effects are huge. What about the social and community impacts? Water supply seems like the big one.
It's fundamental, isn't it? ARD can contaminate surface water and groundwater that people rely on for drinking and bathing.
They're usually toxic.
It can be in extreme cases, like with high arsenic levels. But more commonly, the issue is that the acidic water just tastes unpleasant, metallic. So people abandon that water source, even if it's not acutely toxic.
Which hits developing communities harder.
Especially those relying on rivers or wells. Yeah. And communities that depend on aquatic resources, fish, shellfish, crustaceans for food. The disappearance of these food sources is often a greater immediate concern than, say, consuming contaminated organism.
Although that can happen too with things like mercury buildup.
It can, yes. Mercury bioaccumulation is a known risk in some areas.
The source also mentioned allegations about skin disorders.
Yes, in places like Indonesia and the Philippines. But it noted that subsequent investigations often found these weren't actually related to ARD itself, but maybe other factors. It's important to rely on the scientific evidence.
And then there are the visual impacts, the Red River effect.
Exactly. ARD commonly causes very obvious visual effects. Red or brown staining on riverbeds, rocks, the accumulation of that unsightly gelatinous sludge, the ferric hydroxides precipitating out.
Which probably doesn't help community relations.
Not at all. While the staining itself might not be inherently damaging biologically, it draws immediate attention to the problem. It often contributes significantly to community concern, sometimes outrage. Whether all the concerns are scientifically justified or not, visible pollution is hard to ignore.
Absolutely. And this isn't a problem that just goes away quickly, is it? The source calls it usually a long-term persistent phenomenon.
That's the crux of it, persistence. It can take many years even to appear in some cases, like Tennant Creek in Australia. Or it can develop almost immediately after exposure.
Whoa.
Once it starts, whether it was rapid or delayed, it tends to follow a characteristic profile: a slow increase in acidity and metals, then an acceleration to a peak concentration, followed by a very slow decline over time.
And that decline can take how long?
Decades, or even centuries.
Centuries, wow. This is where the long-term implications really hit home.
They do. Predictions based on the amount of sulfide minerals left behind suggest ARD could continue for hundreds of years at some sites.
The oldest known example is Rio Tinto in Spain. Right?
Yeah.
The river's name literally means Red River.
That's the classic historical case. Copper mining there for centuries led to massive ARD, staining the river red with iron precipitates. Many older sulfide mines around the world have these significant ARD legacies.
And even more modern mines, say from the late 19th, early 20th centuries in the U.S.,
many of those are still being treated today under federal regulations like CERCLA or ARC-ERA. The companies identified as principal responsible parties are legally committed to treating the ARD for as long as it continues.
which could be effectively forever.
Potentially, yes. The Eagle Zinc Mine in Colorado is a case study mentioned, showing that kind of long-term commitment to treatment.
So given this incredibly persistent long-term problem, what can actually be done? What are the proactive steps for identifying, assessing, and managing ARD?
Moving towards solutions, first, you need to identify where ARD is actively happening on a site.
How do you spot it?
Sometimes it's visual. You look for that staining by iron or manganese oxides, or you might see efflorescent sulfate salts, white, crusty deposits. You can even taste them sometimes, though maybe don't make a habit of it.
Okay. Other clues.
You might notice steam emissions if the oxidation is generating enough heat, or smell the acrid odor of sulfur oxides. Simple field tests are crucial too.
Like pH tests.
Routine pH tests, yeah. And paste pH and electrical conductivity, or EC, tests on crushed samples. You mix the crushed rock with water into a paste. If the pH is less than 4, it's acidic. If the EC is high, say over 2 decicemens per meter, it indicates lots of dissolved salts, which often accompanies ARD.
Can you get early warnings from drill cores?
Sometimes, yeah. If drill cores containing sulfides are stored in humid conditions for years, they might start actively oxidizing. You might even see the metal core trays corroding or collapsing. That's a pretty strong early sign.
Okay, so that's finding active ARD. But the real goal is assessing the potential for it before it becomes a big problem, getting ahead of the curve.
Exactly. Prevention is key. Theoretically, any rock with, say, 1% or more sulfide minerals, whether it's in the waste rock, the tailings, or the pit walls, warrants further investigation.
But having sulfides doesn't automatically mean you'll get bad ARD.
No, definitely not. Whether it actually develops depends on a whole bunch of factors.
Such as?
The specific type of sulfide minerals present, their size, shape, texture, how easily air and water can reach them, moisture levels, permeability of the rock pile, oxygen concentration, the pH itself,
Bacteria.
the presence of those acid-loving bacteria we mentioned, and critically, the presence of any acid-neutralizing substances in the rock, like calcite or dolomite.
The rock's own ability to fight back, essentially.
Exactly. And this is where understanding the detailed geology becomes absolutely fundamental. You can't assess the potential without knowing the rocks intimately.
How deep does that geological understanding need to go?
Pretty deep. You need to know how the ore body formed. Metal-bearing sulfide deposits usually come from hot sulfur-bearing hydrothermal fluids, often linked to volcanic activity. These fluids travel through permeable zones in the rock, like faults and fractures, and deposit the sulfide minerals there.
And the surrounding rock changes too. Alteration.
Yes, the hot fluids alter the host rock, changing its mineral composition. So the geological history of an area results in a complex patchwork of different rock types, different weathering zones, maybe multiple stages of mineralization, different alteration zones. Each little pocket can have a unique mix of minerals.
Some high in sulfides, some high in neutralizing minerals.
Precisely. Some might be strongly acid generating, others might be strongly neutralizing, and others might be inert.
So how do they map all this complexity out? It sounds like detective work.
It really is geological detective work. They use all the data from drilling, logging the core, identifying minerals, interpreting geological structures, chemical assays to build a three-dimensional block model of the ore body and surrounding rock.
Like a 3D map showing where everything is.
Exactly. It shows the distribution of all the different rock types, the mineralization, the alteration zones. This model becomes the basis for figuring out the ARD potential quantitatively and for selecting representative samples for testing.
How many samples are we talking?
It varies hugely with the site, maybe 40 to 60 for a small, simple gold mine, but potentially over 400 for a large, complex porphyry copper deposit.
And this model isn't static, it gets updated.
Constantly. As mining progresses and more information becomes available from drilling and mapping pit faces or underground workings, the model is refined. And this updated model then guides how different types or domains of rock are handled, where the potentially acid-forming stuff goes, where the benign stuff goes.
Incredible foresight. So once you have these representative samples, what kind of tests do you run? You mentioned static tests.
Yeah, you usually start with static geochemical testing. These are like screening tests. We already mentioned paste, pH, and EC. The main one is acid-base accounting, or ADA.
Comparing the acid potential to the neutralizing potential.
Exactly. ABA measures the maximum potential acidity, or MPA. That's calculated from the total sulfur content, usually assuming all the sulfur is in pyrite, and will oxidize to form sulfuric acid.
Okay.
Then it measures the acid neutralizing capacity, or ANC. That's typically done by reacting the sample with a strong acid, like hydrochloric acid, and seeing how much acid it consumes or neutralizes.
And the difference is the NAPP, net acid producing potential.
Correct. NAPP is MPA minus ANC. If NAPP is positive, it means the theoretical potential to produce acid is greater than the capacity to neutralize it. So, potential problem.
If it's negative, it's probably okay.
Generally, yeah. A negative NAPP suggests it's more likely non-acid forming. Another common static test is the net acid generation, or NAG test.
How's that different?
In the NAG test, you react the sample with hydrogen peroxide. This forcefully oxidizes any sulfides present. You then measure the pH of the resulting solution and titrate it to see how much acid was actually generated after any internal neutralization happened during the reaction. So it's a more direct measure of the net result.
I see. Both generation and neutralization happening at once.
There are variations too, like a sequential NAG test for tricky samples with high sulfur and high neutralizing capacity.
Okay, so those are the static screening tests. What about the kinetic tests? They sound more involved.
They are. Kinetic geochemical tests aim to simulate the rate at which reactions happen over time. They can be more definitive, especially for materials that give ambiguous results in static tests.
Like what?
There's a kinetic NAG test, which basically just tracks temperature, pH, and EC during the standard NAG test to get an idea of reaction speed.
But the main ones are column tests.
Yes. Laboratory column leach tests are the most common kinetic tests. You pack crushed rock into columns and run water and air through them for an extended period, weeks, months, sometimes years.
Simulating rainfall on a waste dump.
Exactly. You monitor the leachate water quality coming out the bottom over time, pH, acidity, metals, sulfates. This gives you real data on acid generation rates, how quickly neutralization happens, and what the long-term water quality might look like.
Sounds expensive and time-consuming.
They are, so you usually do fewer column tests than static tests, focusing on the most critical or uncertain materials identified by the ABA and NAG tests. Sometimes mines even run small-scale leach pad trials right on site, building mini dumps to simulate field conditions even more closely, maybe testing different cover designs.
Okay, so after all this testing, ABA, NAG, columns, you classify the material.
Yes. Based on all that data, materials get classified into different categories based on their acid-forming potential. Common categories are barren, no sulfides, non-acid-forming, or NAF.
which has negative NAPP, high NAG pH.
Typically, yes. NAF usually has negative NAPP and a final NAG pH above 4.5. Then you have potentially acid-forming or PIF.
Positive NAPP, low NAG pH. The problem stuff.
That's the main one to worry about. And sometimes there's an uncertain or UC category for materials where the tests give conflicting or borderline results and need more investigation or careful management.
Should you subdivide those further?
Oh, yes. You might have a low-risk PAF, high-risk PAF. Some systems combine acid potential with other factors like salinity. BHP Billiton had a detailed classification linking categories like high salinity NAF or high-risk PAF to very specific management requirements.
Right.
Isolate the high salinity stuff to protect freshwater resources, or ensure the high-risk PAF is deeply buried within waste dumps surrounded by NAF material.
So all this incredibly detailed characterization feeds back into the mine plan.
Absolutely. It tells the engineers and planners exactly which blocks of rock need special handling and where they should go to minimize environmental risk.
Yeah.
It's a really integrated process. Can you imagine the geological detective work that goes into this before a shovel even hits the ground?
It's seriously impressive. It's not just digging rocks, it's predictive environmental science on a massive scale. Okay,
Yeah.
so once you've identified the potential and classified everything, what do companies actually do to manage this? There's been a big shift from just tolerating it historically.
A huge shift. Before modern environmental management, ARD was often just accepted as an unavoidable consequence. Now, the approaches are much more comprehensive and proactive.
What are the main strategies?
The source lists several. Tolerance isn't really acceptable anymore. The focus is on minimization or prevention, isolation, maybe in situ neutralization, and then interception and treatment of anything that still escapes.
So ideally, you prevent it from happening in the first place.
That's always the best approach. You try to intervene at one of those 3 stages we talked about: oxidation, leaching, or drainage.
How do you stop oxidation?
The best way is to cut off the oxygen supply. And the most effective way to do that is to keep the sulfide-bearing material saturated with water.
Keep it underwater.
Essentially, yeah. Stored below the water table. The Metmero project in Indonesia did this, placing PAF waste rock from later mining phases into the bottom of pits that were already mined out, keeping it submerged.
Is that common practice?
Storing PAF below grade, below the natural water table in mined-out pits, is definitely preferred whenever possible, compared to building large above-ground waste dumps.
But you often do need above-ground dumps. What are the common measures there?
For waste rock dumps, several techniques are used. You can shape the surface to shed water, then cap it with a layer of low permeability material like clay to limit rainfall infiltration and oxygen entry.
Total encapsulation.
That's an option too, though often difficult to achieve perfectly. More common is preferential placement.
Putting the bad stuff in the middle.
Exactly. High-risk PAF goes in the core of the dump, away from the slopes where air can get in easily, and it's surrounded by a thick layer of NAF material. Compaction is also key.
To reduce permeability.
Right. Tightly compacted layers reduce both water and airflow. Specialized construction methods help achieve this, like paddock dumping, where waste is placed in cells, or bottom-up construction, building the dump in controlled layers.
Are there challenges with these methods, like finding enough clay for capping?
Definitely. Finding enough suitable low-permeability material on site can be a major constraint. Using engineered geomembrane liners is usually too expensive for vast waste dumps. Another challenge is timing the best capping material. Often oxidized waste rock found near the surface gets mined first, but you need it much later for final capping, so you might have to stockpile it, which adds cost.
The Metmero dump example was interesting, using an internal barrier to hold water inside the dump.
Yeah, very clever. A low permeability zone built within the dump acts like an internal dam, impounding water behind it to keep the upstream PAF waste saturated.
What about neutralizing the acid within the dump itself? In situ neutralization.
That's another strategy. It usually involves blending alkaline material like crushed limestone with the sulfidic waste rock as it's being placed.
The Grasberg example.
Right. Case 22.4 at Grasberg, Indonesia. They initially hoped the underlying natural limestone bedrock would neutralize seepage, but it wasn't enough. So they started actively blending crushed limestone with the PAF waste, especially near the surface zones of the dumps, to provide neutralization capacity right where it's needed.
Okay, that covers waste rock. What about tailings? The fine stuff.
Similar principles apply to tailings storage facilities, or TSFs. The main goal is still oxygen exclusion. You can achieve this with a wet cover.
Keeping a permanent pond on top.
Exactly. Maintaining a water cover prevents atmospheric oxygen from reaching the tailings. The alternative is a dry cover.
Like the caps on waste dumps.
Similar idea, yeah. Placing a low permeability capping layer over the dry tailing surface to limit both oxygen ingress and rainfall infiltration, which would cause leaching.
Designing these covers sounds complex.
It is. Cover design has to consider the tailings properties, the waste rock properties if used in the cover, the climate, seismic stability, what the final land use will be. It requires a whole team. Geochemists, mine planners, geotechnical engineers, hydrologists, rehabilitation specialists, all collaborating.
And for other exposed sulfide surfaces, like mine openings or road cuts.
Applying a layer of sprayed concrete, often called shotcrete or goodnight, directly onto those exposed faces has proven really effective at sealing them off from air and water, controlling ARD formation.
Batu Hijau seemed to use a whole suite of these techniques.
Yes, case 22.3 at Batu Hijau is a great example of an integrated approach. Bottom-up dump construction, placing low permeability layers on internal lifts, keeping PAF away from the outer slopes, putting compacted clay under the topsoil on the final slopes, and installing under drains to collect any seepage and route it to sumps for monitoring and potential treatment. It's multi-layered defense.
Okay, so even with all these prevention and minimization efforts, you often still end up with some acidic streams or seepage that needs active treatment, right?
Absolutely. It's rare to prevent it entirely, especially at large, complex sites or older mines. So treatment is usually part of the overall strategy.
During mining, can they just reuse that water?
Often, yeah. During active operations, acidic streams collected from sumps or drains are frequently pumped back and used as process water, for example, in the grinding circuit of a gold mill, where lime is routinely added anyway to raise the pH for cyanide leaching. The alkalinity added in the process treats the acidity.
But after the mine closes, that's when ongoing treatment becomes necessary.
That's when you often need dedicated long-term treatment systems. For small flows, it might be as simple as continuously dosing lime slurry into the stream, but larger discharges usually require a proper water treatment plant.
Are there ways to recover value, like metals, during treatment?
There are some advanced technologies being developed and used, yeah. Things like biosulfide treatment, using bacteria to precipitate metals as sulfides, or using materials like zeolites for cementation. These can sometimes allow for selective recovery of valuable metals like copper or zinc, turning a waste stream into a potential resource. That's very promising.
But the standard approach is still neutralization.
Conventionally, yes, using alkaline reagents like limestone, calcium carbonate, KCO3, or more commonly lime, calcium hydroxide, KOH2, remains the most widely applied and reliable method for neutralizing acidity and removing metals.
How does that work chemically?
Basically, the acid reacts with the lime to form gypsum, calcium sulfate, which is relatively insoluble. As the pH rises due to the lime addition, dissolved metals become less soluble and precipitate out of the water, usually as metal hydroxides.
Like the brown sludge we talked about earlier.
Exactly. Iron hydroxides precipitate first, then aluminum, then copper, zinc, and so on at progressively higher pH levels.
Are there different ways to apply lime treatment?
Yes. There's simple batch treatment for small volumes. Conventional treatment involves continuously adding lime slurry to the flowing stream. And then there's the high-density sludge, or HDS process.
HDS.
High-density sludge. This uses a more engineered treatment plant, often involving recycling some of the previously settled sludge. It produces a denser sludge that settles better and takes up less volume.
But sludge disposal is still a major issue with all these methods.
It's a critical issue, yes. Managing the large volumes of sludge produced by active treatment is a significant ongoing cost and logistical challenge. Where do you put it safely in the long term?
So these are all active treatments needing constant input. What about passive treatments?
Right, that's the other main category. Active treatments require ongoing attention, reagent supply, power, maintenance. Passive treatments are designed to be more self-sustaining, using natural processes, often over larger areas, with minimal operational input once constructed. They aim to mimic and enhance natural wetland or geochemical processes.
What are some examples?
One common type is an anoxic limestone drain, or ALD.
Anoxic, meaning no oxygen.
Right. You basically bury crushed limestone in a trench, cover it to keep oxygen out, and route the acidic water through it. The limestone dissolves, adding alkalinity, neutralizing capacity, to the water without letting the iron precipitate and clog the drain. Metal removal then happens downstream, maybe in an aerobic pond or wetland.
So aerobic wetlands are another type?
Yes, aerobic wetland treatment systems. These are typically shallow ponds or marshes designed to promote oxidation and precipitation of metals, especially iron and manganese. They use a combination of biological and chemical processes, oxidation, adsorption onto sediments, plant uptake, often used after an ALD as a final polishing step for metal removal from net alkaline water.
And anaerobic systems, the opposite of aerobic.
Exactly. Anaerobic treatment systems work in environments without oxygen. They rely heavily on sulfate-reducing
Bacteria doing the work again.
Yep. You create conditions, usually by adding an organic substrate like manure, wood chips, or compost, and maintaining deep water where these bacteria thrive. They convert sulfate in the water into sulfide.
And that helps how?
Two ways. First, the process consumes acid, raising the pH. Second, the sulfide produced reacts with dissolved metals like copper, zinc, cadmium, lead, forming highly insoluble metal sulfides that precipitate out and get trapped in the substrate. It's very effective for metal removal.
That's a fascinating range of solutions, from
Right.
high-tech prevention to harnessing natural processes. But what about the huge challenge of remediating sites that were abandoned long ago, where ARD might have been going on for decades with no one managing it?
That's the legacy issue, the orphan sites. It's a massive problem globally. The source mentions a 1994 estimate for Canada, putting the remediation costs for acid-forming mine waste at around $3 billion.
Wow. Australia's estimate was much lower, though.
Yes, under $50 million back then. Several reasons were suggested. Australia has comparable amounts of sulfidic waste, but many sites are in very remote, arid regions where low rainfall and high evaporation limit the actual generation and migration of ARD. Plus, a lot of historical mining in Australia happened in oxidized zones near the surface, which didn't contain sulfides.
Okay, but why is remediating an abandoned site generally so much more expensive than managing ARD at an active mine?
Several factors just compound the difficulty and cost. First, you often lack basic information. Records about how the mine was built, operated, where wastes were placed. They might be unavailable or totally inadequate. This makes it really hard to even figure out the source and extent of the problem.
You're starting from scratch, basically.
Pretty much. Second, structures might have failed over the years. Tailings dams might have breached, retaining walls collapsed, spreading contaminated material far beyond the original footprint.
Contamination could have spread underground, too. Groundwater plumes.
Exactly. Contaminated groundwater plumes might have migrated extensively over decades, and tracing them can be very difficult and expensive. And finally, there's just the logistics.
No people or equipment on site.
At an active mine, you have staff, labs, earth-moving equipment readily available. For an abandoned site, you have to bring everything in: environmental investigators, drilling rigs, construction crews, maybe even build access roads. Mobilization costs add up significantly.
So given these huge costs and challenges, especially with orphan sites maybe lacking a responsible company to pay, is successful remediation even possible? Are there real success stories?
It's tough, especially financially, because remediation rarely produces anything you can sell to offset the costs. Unlike active mining, lack of funds is often the biggest constraint, particularly for those orphan sites relying on public money. However, the source is clear that many examples do exist where ARD from abandoned sites has been substantially reduced or effectively treated. It is possible to restore the environment, maybe not to pristine condition always, but often to a state comparable to how it was before mining, supporting healthy ecosystems again.
The Eagle Zinc mine was mentioned again here as a success.
Yes. Case 22.2. It's highlighted as a powerful example. Decades of ARD had severely impacted the Eagle River in Colorado. But through sustained remediation efforts, including source control and treatment, zinc levels in the river dropped dramatically, and populations of brown trout, which are quite sensitive, increased significantly. It shows that even really bad, long-term ARD problems can be tackled successfully with the right science, engineering, and long-term commitment.
That's encouraging to hear. So we've really dug into acid rock drainage today, its origins from those oxidizing sulfide minerals,
How common they are, both naturally and especially when exposed by mining.
and its far-reaching impacts on the mine operations themselves, corrosion, safety hazards, but especially the ecological damage to freshwater systems,
And the potential impacts on community water supplies and livelihoods.
plus the visual blight.
Yeah.
And we explored that whole sophisticated range of assessment tools and management strategies, from prevention and minimization through careful waste handling and capping.
To active treatment with lime and passive systems using natural processes like wetlands and limestone drains.
It truly is an unseen legacy in many ways, but one with known origins, identifiable impacts, and definitely evolving solutions.
Indeed. I think the key takeaway is that while ARD is at its root a natural phenomenon, mining activities amplify its scale and impact so dramatically that it requires these very sophisticated, often very long-term management strategies that might need to last for decades or, as we've said, even centuries after mining stops.
Yeah.
And if we connect this to the bigger picture, it really raises an important question for you, the listener. As we continue to rely on extracting resources that are essential for our modern lives, the copper, the nickel, the zinc, even the coal, how do we strike that balance? How do we weigh the immediate economic benefits against these potentially centuries-long environmental legacies? And how do we make sure that the solutions we implement today aren't just inadvertently creating new kinds of challenges down the line?
That's a really profound thought to leave folks with. The sheer scale of the ongoing efforts to manage and remediate ARD worldwide just underscores how critical scientific understanding, careful planning, and genuinely collaborative long-term solutions are for tackling these kinds of persistent environmental challenges. We really hope this deep dive has given you a clearer, more nuanced understanding of this crucial, often hidden issue. Thanks so much for joining us.